Hello and welcome everyone. I am Erin Broberg with Sanford Underground Research Facility. During tonight's event, we'll take a virtual tour of the Ross Hoistroom and the conveyor system with SURF's Mike Headley and Fermilab's Josh Willhite. So you guys are a little early. We started a little bit early. We're gonna give ourselves just a minute to connect to Facebook, start our live stream there, and then we'll get going in both places. I'm gonna give our crew just a minute to get us set up on Facebook so that everybody can join and everybody can be a part of this tonight. All right, so if you're just joining us now, you're in the right place. We're gonna be starting our event in just a minute or two as soon as we've connected with our Facebook live stream, as soon as I get the go ahead. All right, I see more and more people are joining. Thank you so much for being here tonight. We're about to get started. I am here in the Ross Hoistroom at Sanford Lab. We're really excited for all of our virtual tours tonight. You'll be able to see the Ross Hoistroom as well as some pieces of the conveyor that are all part of the excavation system for the deep underground neutrino experiment and the long baseline neutrino facility. All right. Gonna get started in just a second here. Are we going? Okay, I just got the go ahead that we are live on Facebook. So welcome everyone on Zoom. Welcome everyone on Facebook. All right, I want to take a moment at the beginning to thank our Deep Talks sponsors. We have Crow Peak Brewing Company, RCS Construction, Northern Hills Federal Credit Union, and Chuck and Jolene Lichtenwalner. Thank you so much for your generous gifts and continuing support of science outreach and education. Crow Peak Brewing Company is sponsoring tonight's door prizes. We have 3 prizes tonight: a growler with 1 fill, a 6-pack of Crow Peak's locally brewed craft beer, and a gift certificate with a Crow Peak t-shirt. So I'm gonna have Matt bring up the poll. And this poll is only available for our Zoom webinar viewers. So if you're watching right now on Facebook, join us next time on Zoom for a chance to win. So there's 2 important things about this door prize. 1, you have to be 21 years of age or older to enter. And 2, you have to be able to pick up the door prize at Crow Peak Brewing Company in Spearfish, South Dakota. So if you're joining us via Zoom, please select the option to enter yourself, and we will randomly select a winner at the end of the event and contact our winners via email. So we'll close that in about 3, 2, 1. Oh, okay, people are still voting, so we'll give it just a few more seconds. Okay. So this is a really great prize. We're really grateful to Crow Peak Brewing Company for supporting this event. So go ahead and enter yourselves. We'll give you a full minute to do that. All right, now we're closing it. Thank you everyone for entering, and thank you to our sponsors. All right, so I am Erin Broberg, and I'm here with Sanford Underground Research Facility, and I'm so glad that you could join us for tonight's event, where we'll take a virtual tour of the Ross Hoistroom and the conveyor system and learn how this huge machinery will support the excavation for and the construction of the largest particle physics experiment on US soil. So tonight, as always, we would love to hear your questions. If you're joining us via Zoom, please use the Q&A function to submit questions throughout the event. And if you're watching live on Facebook, you can add your questions to the comments section. Our first speaker is the Executive Director for the South Dakota Science and Technology Authority and the Lab Director of Sanford Underground Research Facility. Tonight, he will discuss the historic and cultural significance of this undertaking before we begin our tour. Please welcome Mr. Mike Headley.
Okay, thanks, Erin. Thank you all for joining us tonight. It's exciting. It's a very exciting time here at SURF. as we'll talk about, the mobilization of contractor staff and equipment has started this week, and soon we'll begin major excavation activities to build the long baseline neutrino facility, or what we call LBNF. This evening, my colleague Josh Willhite and I will take a look at the recently completed facility upgrades that will be used to build LBNF, starting with the excavation of over 800,000 tons of rock to create the largest caverns to host the world's largest neutrino experiment called DUNE, or the Deep Underground Neutrino Experiment. Josh is the LBNF Far Site Conventional Facility Design Manager with Fermilab, and Fermilab is the lead Department of Energy National Laboratory for this project. LBNF excavation will be the first major rock excavation at our site since the Homestake mine concluded operations in the early 2000s. And LBNF will be the first underground science space expansion that we've undertaken since we constructed the Davis campus, 4,850 feet underground over a decade ago. As many of you know, the land where SURF is located is sacred to the American Indian tribes of the region. In our planning for this project, a formal environmental assessment was completed, and this assessment process included consultations with the tribes to ensure they were comfortable with our construction plans. As part of this process, we made specific commitments to the tribes, such as the excavated rock that we bring up for the underground will not leave the Black Hills. And to honor this commitment, we're putting the LBNF rock in the open cut on the north end of Lead. Also, the project will be constructed only in areas that have been used for mining previously, so no new disturbances will be generated. The DUNE experiment collaboration is a broad international community made up of over 1,300 scientists from over 200 institutions representing 30 countries. 60% of those institutions are not within the US. So the project is truly international from the start, and we have these groups contributing from this project from all over the world. So we recognize that SURF is an international facility, and it has to be a very welcoming place. As people come here, we want them to feel welcome and to contribute to the work here. And we believe that the world's best science requires diverse voices. One of our core values here at SURF is care for others. And we embrace and honor the fundamental value and dignity of all individuals. We listen knowing that everyone has something to offer and something to learn. So at this time, I'm going to join Josh, and we're going to look at the upgraded hoist room. These hoists were installed back in the 1930s and propelled the Homestake gold mine to become the most productive gold mine in the Western Hemisphere. They're truly a remarkable engineering feat, and recently upgrades installed will power these hoists to really construct the largest science experiment ever constructed on US soil. We'll then take a quick break for questions, and then Josh will give us an overview of the rock handling system that will be used to bring rock from deep underground up to the surface and over to the open cut. So at this time, I'll ask Josh to come over and join us.
All right.
This is Josh Willhite. We will do our best to stay socially distant tonight when we're don't have our masks on. And I'll turn it over to Josh to start the tour.
All right. Thank you very much, Mike. So we're going to start over in this area over here, and I'm going to have our cameraman follow us here. One of the first things you're going to notice if you've been in this hoist room before, which a lot of people watching probably have, is pretty quiet in here. And that's because the way these hoists are powered now is considerably different than the way they were powered historically. So the hum that used to come from the motor generator sets, where an AC motor spun this huge flywheel, one of which is still here. We haven't completely removed it yet. And that big flywheel then spun a DC generator, which was what actually powered the hoist. And so we looked at that system. The motors needed to be refurbished, and we really kind of weighed our options and decided that we wanted to simplify and go with a more modern solution for these hoists. And so what we've done is installed new AC motors. And not very interesting, but behind the cameraman, there's some new variable frequency drives that power these AC motors. And that really replaced that motor generator system. That actually, it makes it quieter in here, which is nice when the hoists aren't running. But it also has a considerable energy savings. You can imagine if the hoists aren't moving, those motor generator sets were still drawing power. So that was a good benefit we got from this system. Another thing I want to point out while we're right here is right behind me, between the motor and the gearbox, you see a vertical disc there. This is a new addition. This is something that did not exist historically, and this is what we call a pinion brake. So because this is the cage hoist, the hoist that moves people up and down through the shaft, we wanted to have a redundant braking system, and really that's mandated by code in modern day here. And so that provides a secondary braking system to make sure that even if the primary braking system were not to function properly, we would have a means of stopping that and keeping our people safe. So now we're going to walk around the hoist a bit, and I'm going to show you some of the other items that we've modified. So as we walk here, we're going to see, should have pointed out, kind of a common theme that you'll see with the modifications that we've done is this blue color. So CMAG Techberg, you can see the name there. They are the company that actually designed and built the upgrades that we've done to these hoists. And in fact, they are the company that now owns the rights to the design of the original Nordberg hoists here. So we haven't changed a lot. These are great hoists. They're very well designed, and we didn't need to change a lot. The reason we changed what you see here, which is the primary braking system, I pointed out the secondary pinion brake, is because the original braking system was a low pressure hydraulic actuation, and the drum wasn't exactly round the way we wanted it to be. And so that means we couldn't control the deceleration rate the way that we needed to make sure that we were really had full control of that speed that we decelerated. So we came in, we replaced the hoist brakes here, the drum brakes on all 4 of the drums. There's 2 hoists in this building. They're identical, each has 2 drums each. And we replaced that with a high pressure, more precise controlled braking system. The other thing I want to point out at this location before we move on to the next location is you can see a kind of an intricate spider system inside of this brake system. That is actually the historic clutch. That allowed us to disengage this particular drum from the gearbox so that you could run either drum independently. This was a friction style clutch, very similar to what is run in a car for people that are familiar with manual clutches in cars. And that means that the friction has to be engaged for that drum to move. And so that's not allowed by modern standards. And so we've replaced that friction style with a positive engagement. In this particular case, the reason you still see this is we've actually affixed this clutch. So we only have 1 clutch on 1 drum per hoist now. We can still move everything independently, but we can do that with 1 clutch. So now we're going to make our way around and look at what that new clutch looks like. And before we get to that clutch, we're going to see a pretty major difference again for those who have been in this hoist building before. You're seeing some new control cabs here. And we're going to actually go inside of those control cabs and see exactly what the modifications were inside there, but this is a good viewpoint to really see the difference here. The platform is at the same level as it used to be, but this used to be wide open. We're in this room as a hoist operator. Now we've got climate controlled cabs that keep the hoist operators comfortable and also protect them from the noise that's generated when these hoists move. So now we're going to move on.
So Josh, maybe to point out for those who have seen the hoists and the old controls and everything that we've been using since they were installed back in the 1930s, rest assured we have saved all that equipment, and we don't have any definite plans for a display or what have you, but we've gone to great lengths to make sure that the historical elements of the hoists that have been replaced, that we've retained those.
Well, thank you very much for that, Mike. That's an important point. So as we move over here, you can see we've got a second hoist here that's nearly identical to the first. And this is where you can see that positive engagement clutch I was talking about. So unlike the clutch you could picture with a vehicle, you can see there's actually gear teeth inside of here. And that single blue arm that you see there has 2 opposing gear engagement teeth that actually make sure that there's absolutely no way when that's engaged that it could slip. And so again, that meets modern standards. Another thing to point out on the production hoist, just while we're here, you're going to notice that the brakes on this hoist are the original. There's no blue there. There's no CMAG Techberg sticker. That's because this hoist is strictly for moving rock. And so that precise control of the braking isn't as important on this particular hoist as it is on the hoist that handles people. So with that, we're going to go ahead and walk our way up into the control cab here, and I'm going to introduce you to Laurie Adkins-Heydon, and she's going to talk to you about the modifications that have been done here. So we'll get up in
just a
here.
moment.
So Laurie, you want to introduce yourself and talk about your background here and how the hoists are working?
Hi, I'm Laurie Adkins-Heydon, and I have been working on the hoist off and on for a total of 25 years. We have many of us here with a lot of years, so I feel honored that they chose me to do this. We have changed over the old hoist to a new electronic, basically, and hydraulic system. It is very interesting to run. We are learning on it, and it is going to be wonderful once everything and the bugs get worked out. We're all wonderful, and just looking forward to extending my time on the property with the lab.
So maybe give a little overview, Laurie, on how the hoist operates and the controls. Your
Sure.
all new computer controls.
I know. Well, if you look at this one, this will actually show you the shafts itself. This one is the man cage. And then this one, of course, is our counterweight. As one goes down, one comes up just to balance itself. All of these are the levels that we have in
Did you shut that
the shaft. Most of everything goes to the 48 or will be going to the 48. We do have some work with another company, Tyson, going to the 3650 to make sure that we can get some of their equipment off on the ramp. We do our checks daily on the cage and the skips. Our shaftmen are up there and they're our partners in crime, so we make sure we get everything right. Well, I don't know. This right here actually shows you the exact footage that we're at in the shaft. We don't basically go off just the numbers of the levels per se. We actually go off the footage, which is the actual footage in the mine. And it's off because when they did the measuring on the Ross, they took it off of the Ellison, and the Ellison was at a lower level than what the Ross Hoistroom was. So that's why the levels are off a little bit.
So an older shaft kind of set the levels for all the ones that we're operating today.
Correct. So in order for them to get their computer correct, for us to get to the levels properly, that's why we have different numbers written up there. And then this is just a drive control that we can look at to see if our brakes are ready, if we're ready to go on our throttle right here, whether we're going in or down or up in the shaft. These are all different modes that we can be in. In the off mode, if you push that, it's just kind of another safety valve to put on if you're going to leave the platform. The e-stop is also another one. You can just push it and it'll automatically, nothing will move.
So the emergency stop.
Correct.
Yep.
So you just pull that back up and we clear the fault. This will read, of course, no faults, your brakes, whether we're lowering or hoisting. We have a dead man, which is right up here on our right foot. And we have to compress that. It's similar to the old motors underground that we used to take supplies and men and women back and forth underground. So we have to have that suppressed when we're running the hoist to all the different levels. And then we have so many different screens on this to show. This is a tech zoom. And on this one, it shows us what our pumps are, if we need to look up at motors, what the set speed is at. And I mean, it's pretty much all at our fingertips. It's very interesting. It's quite informative, actually. And then we actually have a log here for alarms, like if we're coming on shift, to show us what happened or what we need to be aware of, besides the communication we do between shifts with our partners. So we normally run in a drive screen, and then these are just the permissives, which I explained already, and then the mode in case you need to change. But normally we run in manual for loads and personnel when we have just men on. And our speed is 500 feet per minute right now.
Sorry to interrupt you, Laurie.
No problem, sorry.
So I think we'd like to have you actually run the hoist
Okay.
and show us how it works. Before you do that, I don't know that any of us have actually mentioned how new this system is. So we literally we shut the hoist down on January 18th. We spent about 2 months installing all of these different components that we've been looking at today. And we've spent the last month really getting the operators comfortable with the system and commissioning all the components. So it's been working pretty well for us, but you're just gonna have to bear with us because it is a new system. And so I'm gonna turn it over to Laurie, and if you could actually disengage the brake and move the drums a bit for us. I think I've worked here a long time, and it's always impressive to see these hoists move.
If you look right now, our cage is actually located between the 1250 and the 1400. This is just a line to tell us where our work area is, and you can move it by just highlighting the area and it'll follow it down. They'll put that in the system just to help us visually. So I will go ahead and proceed down with the cage. So normally, if we're on a level, we will say to our shaftman, or they will say to us, cage to the whatever level they need to go to, 4850. We repeat that, and then they'll say cage lower, and then we give it power and go down the shaft. So this is our throttle. You can hear the fans kick on.
Hear the motor come online, the drive motor?
Can it come online?
Yeah.
As far as what? I'm sorry.
Oh, that it turned on.
Oh, yes.
Sorry, I was just
No, you can
saying what
hear
the
it.
noise was in the
That's
background.
okay.
So.
And then our max speed, like I had said, is 500 feet per minute. We don't go until we see all three of these red. Otherwise, it may kick out because we're kind of over speeding, which we don't want to do that if men are on there or anything. So we are traveling down the shaft now. And if you watch this will show you the depth of the cage, and this shows you the depth of the counterweight. Around 2950 is when they are equal in the shaft. That's where we do some of our brake tests with the mechanics on a weekly or monthly check.
So we should probably mention is with these upgrades, one of the things we'll be doing is increasing the operating speed of the shaft, likely going to something, and this is something still our engineers are working through, but somewhere probably around 2,000 feet per minute. So instead of taking 10 minutes to get roughly to the 4850, that'll be cut down to about a third of that time or so.
Correct.
Right.
Correct.
And these hoists are actually designed to operate at up to 2,500 feet per minute. That's almost 30 miles an hour, straight down, straight up. We don't need to go that speed, and so that's why we talked about we're still working on exactly what speed we're going to end up at, but it'll be considerably faster than this. And Laurie can tell you, it's pretty exciting to see these drums spin when we're going at 30 miles an hour straight down the shaft.
When I broke in as an operator, we did travel 2,500 feet per minute. And when you first walked in and saw that, you were overwhelmed. Once you ran it, and we didn't even blink an eye at running that speed. But when we got it up to that last week, it was like, holy moly. So it is quite impressive to know we used to run at that and how slow we've gone because of the rehab on the shaft itself. So it is kind of cool to be back at the same speed, but kind of scary butterflies in the same respect. We do have a reduced speed on here, and if we touch that, it brings the cage to a very slow speed without a jerk or anything. So it brings it down in case they want to look at something in the shaft, or if we're doing inspections in the shaft. It's just a nice speed for them to go, and then we can actually pull it back and move it at such a minimal speed that it's kind of fun.
All right, so very good. I think at this moment, we're going to take just a moment and take a few questions before we move on to the next segment. So I'm going to go to Erin and see what kind of questions we've gotten so far.
We've got some great questions coming in. So one of the first ones is for Laurie. What is the biggest difference between the old system and the new for you as a hoist operator?
Probably the biggest one would be the hands-on, because we actually had the throttle and the brakes that we moved. Now everything's within our fingertips, and the new technology, it's quite fantastic, actually.
Yeah, so a question to follow up on that is, do you feel you have more control with the old or new system, or is it relatively the same across the board?
you know, of course, working on a hoist for 25 years, you feel like you have a better response. However, I think technology is probably a few milliseconds quicker, but I don't know. I think once we're comfortable, I mean, not that we're not comfortable now, but once we get more used to it and are running it more, I think they're going to be pretty equal.
Of course, awesome. So another question we had was, will hoist operators typically be on the hoist, operating the hoist 24/7, or will it be a different schedule? So will there always be someone seated at that chair?
Yes, there will. There will. This is kind of a hub for people to get in and out of the mine. So in case of emergencies or any type of a shutdown that's not expected, having someone in the hoist room to manage anything that could be a problem, I believe is necessary. So yes, it'll stay the same, I believe.
I should mention too, are the code requirements that we have to meet require that there's a human in the loop. So we can't, even if you could fully automate them, we still need to have an operator here making sure things are operating properly.
And I would add that during the construction of LBNF and Dune, they're not going to get a break. We're going to need them 24/7. So,
yeah, I was afraid of that.
But in general, probably should mention our hoist operators, along with the people who work underground, generally work a 12-hour shift. They work 7 days in a row, 12 hours, and then they're off 7 days, and then that repeats.
Yeah, so another question from someone who seems to be familiar with the system is, the Lilies were an alternate emergency stopping system. Are they still active or have they been replaced?
Actually, the Lilies our old Lilies are no longer part of the system. They have upgraded it to use them as the hydraulics and the tech support that we have for the screens. So they're still introduced in there. Can you help me to see
I
where
would say
they
basically
are?
like an electronic version of the Lily as part of the system now.
yeah, the name for it now is called a Superior Hoist Electronic Protection, or SHEP system. And that actually serves the same purpose electronically. It's not mechanical like it was previously, but we have the same types of protections on the hoist as have always been there.
And with us sitting here, we actually have the cabinet is open, I apologize, but we actually have a reading that is for the SHEP itself here that is very similar to this, but if there's a different code that faults, then we can read it there and be within reach to reset or continue what we need to do to make it right.
So this may be the most important question of the night. Which chair is more comfortable, the old or the new?
Oh, Lord. You know, they have been so kind and generous to give us many options over the years of 15 that I've been here. Honestly, I like this chair. I just have to figure out how to reach the dead man and be comfortable with my short legs. So
I'm sure they'll figure that out.
yes, they
you.
will.
Yep.
But no, I would say this is a great one.
Yeah. Okay, I think this one would be a question for Mike, but are you doing the same upgrades to the Yates hoist room as well?
We're not now. We do have a long-term facility upgrade plan, and that is part of that plan that within a few years from now, we'll be introducing those changes over at the Yates too. Yep, okay. Absolutely.
Well, we still have some questions, but this is a brief Q&A that we will finish at the end of our talk. So we'll go ahead and pause the Q&A session. Keep sending your questions in, and we'll answer those a little later on.
And don't worry, we will have Laurie with us when we answer questions later. So
thanks.
We're going to make our way back out of the cab here, and we're going to make our way to talk about the rock handling system. But before we get there, I just want to pause for just a moment at a pretty important historic plaque here. I had mentioned Nordberg hoists earlier, and you can see here that that's not made up. 1933 is when these hoists were built and installed here. And the incredible maintenance done by Homestake and now the Sanford lab has kept these hoists in good operating condition for all of those years.
And one of the fascinating things that as these were being upgraded, we got to see at least electronic copies of some of the memos and letters that went back and forth between Nordberg and Homestake back in the day, and about the ordering and the installation of the hoist. It was really fascinating. Right. All that history has been preserved by the company.
The cost is just slightly more than it was in 1930s to do this. So we're going to go ahead and move over here, and we're going to switch to a video that I'm going to give you a little bit of narration on how we're going to move the rock. So take the mask off here while we're separated. So we've got, of course, as Mike had mentioned, about 800,000 tons of rock, a little bit more than that we need to move to create these spaces for LBNF and dune. And so as Matt starts the video here, we're going to start it off with a big bang. That's for my physics colleagues there. And so it all starts out with drill and blast excavation, very similar to what was done at Homestake for many, many years. So you blast out the rock, and then you're seeing a very, very rapid mucking process here where loaders come in and move that rock. We're going to flip to, this is actually at the facility. This is the drilling that was done to create some excavation already at the facility, and that's the mucking happening. So they're driving through the drifts here, and we had to store that muck during the pre-excavation phase that we just finished because the systems I'm going to describe from this point on weren't in place yet. So they brought that muck and stored it underground. Now they're going to move it to the Ross shaft. And so you can see the Ross shaft here. We zoomed in. And we're going to zoom out a little bit here in just a moment and see what's called our temporary grizzly system. And the grizzly is just a series of bars that keep too big a rock. So 14-inch rock is what we're planning from falling into the ore pass. So it's covered right here. And the next video here you're going to see, or image, is this is actually this last week dumping rock through a even more temporary grizzly into the ore pass. So thanks for pausing it there. So now at this point, before we move on, that rock has been dropped in, and we screened that a little finer just to help understand that, because this was completely emptied out. And so we want to create a little bit of a cushion with some smaller rock before we start dropping any larger rock in. So this is a very large ore pass, some great photographs here taken by Matt Kappas with the Sanford lab. So the first one was looking up, this one's looking down. Now we're looking up again. If you just pause it right there for a moment, Matt. What I want to point out here is there are two legs to this ore pass system. On the left-hand side, you see this white structure, and the white structure is actually a system that was installed by our contractor, Kiewit Alberici joint venture, to be able to access into this ore pass. So this was completely full of material when we started, and they had to work their way down, empty it out, and put all of these rock bolts that you see in to make it safe, really, for them to continue to remove the material down below. So that was a big part of the process, was just getting it safe so they could empty it out. And at the bottom of this, we had to rebuild a wall. And now if you want to go ahead and keep playing, on the other side of that wall is a skip loading system. And so we're seeing some gates here. These chains are to keep material from flowing too fast through these chutes that you see. And these chutes have a gate at both the top and the bottom. There's an example of one of the gates. So if you can picture, there's basically a space between two gates. The top gate opens, bottom one better be closed, that's all programmed. That allows that space to fill up with rock. Now the top gate closes, the bottom one opens, and you've got instantly filled skip. And the skip is the bucket that brings that rock up to the surface. So that's where Laurie comes in and hoists that rock up to the surface. So we're back in the control cab here. Of course, we would be skipping in this case, so we're bringing the other hoist up and bringing that skip up to the surface. So this goes again at about 2,500 feet per minute. Here's one of the skips actually coming into the scrolls inside the head frame. So this is how the skips dump. Now this one's empty. This is a testing that we did. But you can see how it tilted, and there we can see where it actually opened up, and that allows that material to drop into the crushing system. And so that really is the first step in the process, right? So the first thing we need to do is get that rock up to the surface. The next step in the process is what we're going to watch now, which is to crush that rock. And really the only reason we need to crush that rock is to make it small enough that we can convey it. Historically, Homestake needed to crush it very fine to mill it, to extract gold. We don't need that. We just need to put it into a conveyor system. So if you pause just there for a moment, Matt, right behind these huge chains, and there's a person in that picture there, if you don't see him, for scale, these are like ship's chains, ship anchor chains. Behind those chains is where that skip dumped the rock. These chains, as you can kind of see here, are on a turning shaft. And so they hold that material back and they slowly rotate and keep feeding that material into a crusher at a controlled rate. So go ahead, Matt. So there's just a zoomed in picture of those chains. And they're flowing that material into the crusher, and it's really hard to get a good picture of the crusher, but this is the top of it. This is a jaw type crusher. So we removed the historic gyratory crusher and installed a jaw type crusher. It's just like the name sounds, it's two jaws that kind of move together and crush that rock. It's all controlled from a new control room, which is what you're seeing here. And so this is sitting right above the crusher, and you can see some of the control screens. This person is actually operating those skip loading system as well. So after that crusher, it falls into, anybody familiar with the system may recognize the top of the old cone crusher. We don't need to crush it that fine. So we actually just remove the cone from that cone crusher, and it's just a really robust chute now. So underneath that is a second conveyor, and we're looking at the tail end of that conveyor here. So that material is dropping down onto this conveyor and gets pulled through. Now we're looking where it's getting pulled through to, and goes up an inclined conveyor to a diverter gate. And so we're going to see that diverter gate right here from the side view, and we're going to rotate around and see it from the front. And so there's that diverter gate, and this is really an important thing we believe for our community around us here. So underneath this diverter gate is a very large bin, and it's split in half. And so we could have said, well, let's just use half of that and not need that diverter gate. But with that diverter gate, we can use all 5,000 tons of storage capacity below that gate. And by using that, we can actually store enough rock that we don't have to run overnight and we don't have to run on the weekends. In general, we might have to catch up at some point because something went wrong, but in general, this is what allows us to not run. And we're going to see in just a minute why that's important, because the conveyor system goes right through our local community here. So we want to make sure that we're being respectful to that community. So at the bottom of that bin is where we load onto a conveyor system. Now, historically, this was loaded onto rail cars and transported that way. We are loading it onto a conveyor. So we started out with some big orange air cannons. There's a picture of them there. That helps keep that material moving in the bin. That helps flow material onto these vibrating feeders that actually control the rate of feed flowing onto the belt conveyor. So now the material's on the belt conveyor. One of the things we worry about is, did a bucket tooth or a rock bolt get onto that belt that could tear it up? So we've actually got a magnet here. That's what you're seeing here, this Irias magnet. This is to make sure that we pick up any metal that gets on that belt before it could possibly tear the belt. Then after that, we've got a metal detector, which is in a failure mode right there because we're not running. But this is the actual metal detector part. And that catches anything that didn't get picked up by the magnet, and that stops the belt. This is a long belt, takes a lot of time to replace it, and of course it's not free either. So one of the other interesting things here is the tramway that this conveyor runs through is not a straight path. This is a tunnel that actually comes out from the underground, and we're going to see that in a minute. But it's not a straight tunnel, so we actually have curves in that conveyor, and you saw that in the previous clip here. So we're walking along that. We had to re-secure the ground throughout this tramway to make sure the conveyor was protected. Had to replace a little bit of a snow shed. That conveyor makes its way all the way out through a portal here that we also rebuilt. That's 2-foot thick concrete there, and into a transfer building, and that's what we're seeing here. At that transfer building, the material drops right here from the first belt, which is what we're seeing mostly. This is the very end, and it drops onto this second belt. And so this second belt is what carries that material to its final resting place. And so this is the overview of the belt, and you're going to see it's a pretty impressive structure. It's entirely elevated. That helps us deal with the topography. It also has an added feature that it makes it a little bit more secure because we are pretty close to the local community. Makes it harder to get to. It's covered the entire way to keep anything from coming off and to keep snow and rain from getting on it. It's fully enclosed even where you walk. What we're seeing here is it goes over the highway. The material gets transported all the way to this open cut, and we've got a great view here. That yellow piece that's kind of dangling at a slight angle there, that's an extendable chute. So that lowers about 45 feet. and that prevents a very high free fall of material. That gets it down close to the top of where the pile will be, and just pause right there, Matt, if you would. And from that point, that material just cascades into the open cut. We don't have to touch it again. It will flow down that steep face. And as just kind of a neat side note, we did a engineering study of this. It actually helps buffer that particular space. So it's already secure, but this just makes it even more secure. And something people always wonder is, well, how much of the open cut's going to fill up? 800,000 tons, that's a lot of rock. Well, compared to what Homestake did, that's not a lot of rock. So this is less than 1% of this entire open cuts volume. And in fact, with the full 800,000 tons of rock placed inside of there, that rock will just look like a little pile. And due to where it's located within the open cut, it's not going to be very visible either. You're going to be able to see it from the nearby visitor center. And there's a couple of other strategic locations you'll be able to see it. But for the most part, it's not really in people's views. So that's a good view. We're going to go ahead and whip around and go ahead and finish that out, Matt. I think you got a little bit more video to show kind of the perspective with the lab, or did I? That is it. So, all right. So with that, I think we're going to open it up for the second round of questions here. And hopefully we've got some good ones.
We've got a lot of questions.
A lot of questions.
We'll go ahead and welcome our three answerers to the view.
So, a mask up here since we're standing close together.
All right, you guys ready?
Sure.
We've got a lot of questions. All right, one good question that we've got about 3 different times in 3 different ways is, how much rock, how many tons of rock is transported in one of the skips at one time? So
that's a really good question. So it depends a little bit on the density of the rock. Each skip is 6.5 cubic yards. So that's a fixed quantity, but depending on how dense the rock is, it's anywhere from 8 to 11 tons per skip that gets transported. And at the speed of these skips, if we were going 100% full speed on the hoist, which as we talked, we may not be going, we're going to dump one of those skips every about 3 minutes. It's a very rapid process and lets us move a lot of material in a hurry.
Right. And here's one for Laurie, I think. How many hoist operators are there in total at Sanford Lab? Perhaps you or perhaps Mike have the answer to that one.
No, I'm counting here. Huh. I think there are 11.
Over here.
At the
Oh,
Ross.
just at the Ross. I'm so sorry.
Yeah.
At the Ross itself, there are 10 of us, 9 of us, 9.
Yeah, I want to say we're probably 16 to 18.
Okay, that gives people a good estimate to see how many people are operating that.
And of course, that's because of that 24/7 coverage we already talked about. They're not all here at once.
Awesome. All right, another one for Josh. How long is the conveyor?
So the 2 conveyors put together is a little over 4,000 feet. The first one is, I should know this off the top of my head, 2,800 feet, and the second one is 1,400, somewhere in there. So it's a long ways. Certainly not the longest conveyor in the world. Many people in Lead may remember that the original conveyor that brought rock from the open cut over used to have a sign that said longest pipe conveyor in the world. We're not quite to that level.
All right, this one's for Mike. Is there an accounting of people going in and out of the underground so that we know how many people are underground at one time?
There is. We have a underground headcount limit of during normal operations of 144 people. And so that's, if you count all the noses that are underground, that's the maximum we can have. And that's all driven by how fast we can get people out in case of an emergency. So we try and base that number is based on how many people we can get out in an hour. And so we have a system that keeps track of all the people who are planned to go underground. And we still use the old brass tag system, something that's kind of exciting. We're working with a commercial company to start to use a Wi-Fi based tracking system. So we'll know Not that we want to be big brother and watch people all the time, but where people are at. So in case we have an emergency, it's much quicker for us to understand where people are at so we can facilitate getting them out as quickly as possible.
Perfect. And this one's for Laurie. How long did it take you to learn to become a hoist operator? What was that training like?
Well, back in the day with Homestake, we were trained on 9 hoists overall, and they gave us a time limit of, trying to think here, I think we had 9 months. They guesstimated a month per hoist, but when you got used to the Yates, it's very similar to the Ross, so you usually could skim quicker through those once you got the hang of them. So, yeah.
All right, and people are noticing the springs behind you, the red and white over here on the hoists. Can we have
Sure.
maybe Josh explain what that is?
Absolutely. I should have pointed that out when I was pointing at these. So these are called spring engines. Never quite figured out why we call them spring engines, but the way these brakes work, you actually have to have power to disengage the brakes. And so the springs keep them engaged until you put hydraulic power to them to disengage them. So that's really what they're doing. They also, as you may have been able to see in the video when we started, they help kind of cushion how that brake moves. And it's really kind of fun to watch them engage and disengage because they kind of bounce a little bit, and they really have great control over the speed of the braking.
And they're hydraulic driven, right?
Right. It's hydraulic driven to disengage them, spring driven to engage. Yep.
Right. People are noticing a lot of things in this frame. Somebody has noticed that you have an extra tag on your hard hat. Can you explain what that's for?
Oh, sure. That's it's called a hard hat tether. We work above a 5,000 foot shaft, so I don't want to lose my hard hat down the shaft. And so when we're working out in the field, we require those, and I'm just kind of used to wearing it.
All right. We're going to go back to Laurie. Did you have to be retrained on the new hoists in the Ross, this new hoist system?
Oh, absolutely. No, they want to make sure that every hoist operator is comfortable with it before they jump on, because we have the responsibility of men on the other end that we want to go home safe every day, as well as the loads they need to move for the different companies. So yeah, every load is treated special.
All right. Is there a battery backup or other power in case of an outage? I'm not sure who to direct that one to.
So I can take a stab, and Mike can
Sure.
jump in. There is no standby power system for this. There's no backup. Part of the reason for that is the power reliability at this particular site is exceptional. Homestake had their own power plant at one point, and because of that, there is a distribution system that connected to that power plant that's kind of unparalleled in the Black Hills. And so we've got 3 or 4, depending on how you count it, redundant feeders that feed the facility. And those are powered from, I forget how many different power plants can get to this site. So kind of an interesting factoid, I've been working at this site for about 11 years, and the total power outage downtime is measured in seconds in that entire period. So it is something that we will likely consider in the future. Mike, maybe
Yes.
talk to that, but that's why we didn't just jump on having that backup power supply.
Yeah, we have talked about that as a future upgrade. So it isn't on in the budget right now, but I mean, a couple of interesting facts. When we had Winter Storm Atlas a few years ago, and so many in the region lost power, we did not. We had power all the way through that. And actually through the snowstorm we had a couple of days ago here that took out power in Lead and Deadwood, the site was still up and operating. We did not lose power. So it's a great example of how we're leveraging the really robust infrastructure that Homestake put in, and make sure that we have really reliable power. So,
and one other thing I'll just add is, one of the benefits of having this AC motor with a variable frequency drive system is we can control the amount of current draw. So if we ever do go the way of adding standby power, we'll have the ability to move slower, but we won't need these are 3,000 horsepower motors I'm standing behind. We won't need a 3,000 horsepower generator to move them.
Do you anticipate any dust arising when you dump the rock into the open cut? And if so, is there a way to mitigate that?
So we have designed in ways to mitigate that. One of the ways is that chute that I pointed out in the video that really controls the free fall distance. We also have water supply to the head of the conveyor that would allow us to spray water on. Now, obviously that's not the best solution in the middle of winter in Leeds, South Dakota, but it is a solution through the summer. We have dust control at the transfer point between the two conveyors where it's actually a suction type dust control to make sure we don't generate dust there. And so it is something that we've given a lot of thought to, and we have monitors to make sure that we're meeting our requirements for that. And if we're not, we'll deal with that.
Right. One question says, how loud is the hoist room when the hoists are operating? And we heard that a little earlier, but I'm wondering if we have that measured in decibels?
Not
Maybe
yet, they have not.
Yeah, I can tell you a very unscientific look at my Apple Watch that has a decibel reading. It gets to be about 87 decibels. If you're standing near the motors, that's where most of the noise comes from, is actually the cooling fan on the motor. It's not the motor itself. It's the fan that's keeping the motor cool.
So Laurie, this is another one for you. Of the, I think you said 9 hosts that you were trained on, or hoists that you were trained on originally, did you have a favorite?
No, I guess I did. I loved 7 shaft. I thought that was just, you know, it was deep, it was dirty, but it was fun. It was fun to run it. So yeah.
You were supposed to say this one.
Oh, and then on top of it, number 2 would be this one.
Good cover, good cover. All right. Yeah, so another question says, did the hoist cable get replaced as part of the upgrade?
Yes, the rope.
Go ahead.
Yeah,
Mike.
I'd be happy to. Yeah, it did. So the ropes on the hoist that we looked at, what we call the cage hoist or the service hoist, those ropes actually, every 2 years with the way in which we used to attach them to the conveyances, we would have to cut off a portion of the rope and reattach it because we weren't able to do our normal non-destructive testing on it. So eventually those ropes got too short, and we got to the point where the ropes on this hoist were too short, and just in the last few months have replaced those with new ropes. The ropes over on the what we call the production hoist or the skip hoist, those ropes have been in service actually the whole time that we've been operating. We've not had to change them, and we have a company come in, independent firm come in and do a non-destructive test on the ropes every 6 months. That's a code requirement for us. And as they get to the point where the strength is deteriorated, then we plan a change out. So bottom line, 2 of the 4 on these hoists have been changed out in preparation for construction.
All right. So we'll go ahead and ask one more question. I think this one will go to Josh. How long in months or years do you think it will take to do the excavation?
So the actual drill and blast excavation, according to our schedule today, is roughly 24 months, so 2 years. And then after that, we have to pour concrete, and that's going to take almost another full year. And then after that, we have to put all the power and lights and everything you need to really power and supply an experiment. And that's going to take about a year. And then the detector installation starts. And so this is a pretty long-term project. The detectors are going to take a couple years each. There's 4 detectors that fit into the caverns. And after they're operating, the plan is to operate for at least 20 years and take data. So this is really a long-term project for this community. It's going to take a long time to build it, and once it's built, it's going to run for a long time and hopefully change our understanding of science.
Awesome. Well, I'm going to go ahead and step into the frame here. You guys can stay here for a second. Can people see me now? A little bit over. All right, great. Well, I want everybody to see me because I want everybody to see this picture. It is a picture, if you can see, this is the Kurt Canyon, and it's black and white. On the top is the Ross head frame. And so we are standing just a little bit down the hill on the other side, but we want to give, you guys don't have to share this, we have 3 copies, but we want to give one of these to each of you to say thank you for helping us tonight. And I think it's really fitting because it's got a little bit of snow on it. We had snow a couple days ago, and this is right where we're at, and this is a beautiful view of the facility. So You all get one of these as our thank you.
Cool.
So
Thank you
Thank
very
you
much.
very
thank
much.
you so much. I'm going to go ahead and say a few more things. I want to say thank you again to our Deep Talk sponsors and to the Sanford Lab communications team that made this event possible. I will end with a reminder to join us on Thursday, May 13th for our final Deep Talks event of the season. This final event will be out of this world, literally. We have Dr. Luther Beagle from NASA's Jet Propulsion Laboratory joining us to discuss the Perseverance rover's first few months on Mars. So watch for information on our website and our social media channels for how to join that. A recording of this talk will be shared on our Facebook, Vimeo, and YouTube channels. If you have more questions, go ahead and comment. We'll try to respond to as many as we can. When you leave on Zoom, you'll be given the option to take a survey about your Deep Talks experience, and we'd love to hear what you have to say. So please do leave us some feedback using that survey. Thank you again so much for joining us. We'll see you again on May 13th.